Imagine a theory so grand, so complete, it explains everything in the universe, a single elegant framework that unifies all the forces of nature, all the particles, and all the phenomena we observe. From the smallest atom, with its intricate dance of electrons, protons, and neutrons, to the largest black hole, with its immense gravitational pull that warps space and time, this theory would hold all the answers. It would seamlessly connect the quantum world with the cosmic scale. It would be the holy grail of science, the ultimate triumph of human understanding. Imagine the accolades, the Nobel Prizes, the textbooks rewritten to accommodate this monumental breakthrough. Sounds impressive, right? There's just one tiny problem. It's probably wrong. The history of science is littered with grand theories that seemed perfect only to be overturned by new evidence. You see, science isn't about finding the perfect answer. It's a method, a process, a way of thinking that prioritizes evidence over certainty. It's about asking the best questions, questions that lead to experiments, observations, and more questions. It's a never ending cycle of curiosity and discovery. Science is a constantly evolving process of discovery, a journey towards understanding the universe and our place in it. Each experiment, each observation, each piece of data adds a new layer to our understanding. And like any good adventure, it thrives on the unexpected. The most groundbreaking discoveries often come from the most surprising places. It's about embracing the unknown, challenging assumptions, and being willing to change our minds when the evidence demands it, and refining our understanding with each new piece of evidence. Each new discovery, no matter how small, brings us a step closer to the truth, because the most exciting discoveries are often the ones we least expect. They remind us that the universe is far more complex and wondrous than we can ever imagine. And that, perhaps, is the ultimate beauty of science. Let's take gravity, for example. It's a force we experience every day, yet its true nature is far more complex and fascinating than it might seem at first glance. We all know the story of Newton and the apple. It's a tale that's been told countless times, symbolizing a moment of profound insight. But what we often forget is that Newton's law of universal gravitation, while groundbreaking, wasn't the final word on gravity. Newton's equations described how gravity works, but they didn't explain why it works that way. Fast forward a few centuries, and along comes Einstein. With his brilliant mind and revolutionary ideas, he changed the landscape of physics forever. He completely revolutionized our understanding of gravity with his theory of general relativity. Instead of viewing gravity as a force between two objects, Einstein proposed that massive objects cause a distortion in space-time, which we perceive as gravity. Einstein didn't just refine Newton's ideas, he fundamentally changed how we view gravity, not as a force, but as a curvature of space-time itself. This was a radical departure from the Newtonian view and opened up new avenues of thought and experimentation. This evolution of our understanding of gravity highlights a crucial point about scientific theories. They are not static pronouncements of absolute truth. They are dynamic, ever-evolving models that we constantly test and refine based on new observations and evidence. They are dynamic, ever-evolving models that we constantly test and refine based on new observations and evidence. Each new discovery adds a piece to the puzzle, helping us to build a more complete picture of the universe. The story of gravity doesn't end there. Even today, Our understanding of gravity is still evolving. Physicists are constantly pushing the boundaries of what we know, exploring new theories and conducting experiments to test their ideas. Today, physicists are grappling with questions about how gravity works at the quantum level, a realm where general relativity and quantum mechanics, the two pillars of modern physics, seem incompatible. This is one of the biggest challenges in modern physics, and solving it could lead to a new understanding of the universe. The quest to understand gravity is far from over. As we continue to explore the cosmos and delve into the mysteries of the quantum world, we may one day uncover the true nature of this fundamental force. Until then, the story of gravity remains one of the most fascinating and ongoing sagas in the history of science. So, why can't a scientific theory be 100% true? This question often puzzles many people, especially those who are not deeply involved in scientific research. The idea that something as rigorous and methodical as science could be inherently uncertain seems counterintuitive at first glance. The answer lies in the very nature of science itself. Science is not about absolute truths, it's about building models that best explain the observations we make about the world around us. These models are constantly being tested, refined, and sometimes even replaced as new data comes to light. Science is an empirical endeavor. This means it is grounded in evidence and observation. Unlike other fields that may rely on abstract reasoning or subjective interpretation, science demands that claims be backed up by observable and repeatable evidence. It relies on observation, experimentation, and interpretation. Scientists observe phenomena, conduct experiments to test their hypotheses, and interpret the results to draw conclusions. This process is iterative and ongoing, with each new discovery building on the previous ones. We gather data, formulate hypotheses, and test them rigorously. This rigorous testing is crucial because it helps to eliminate biases and errors, ensuring that the conclusions drawn are as accurate as possible given the current state of knowledge. But no matter how much data we collect or how many times an experiment confirms a theory, there's always the possibility of finding new evidence that challenges our current understanding. This is because our knowledge is always incomplete and there is always more to learn. Think of it like this. Imagine you're exploring a vast, uncharted jungle. The jungle is dense and full of unknowns, much like the universe of scientific knowledge. You've been hacking your way through the undergrowth for days and you stumble upon a clearing. This clearing represents a breakthrough or a new discovery in science. In the middle of the clearing stands a magnificent tree, its branches reaching toward the sky. This tree symbolizes a well-established scientific theory, one that has been supported by extensive evidence and research. You might be tempted to declare, "This is the largest tree in the jungle." This is akin to scientists feeling confident about a theory that has withstood numerous tests and challenges. But how can you be sure? Just as there might be a larger tree hidden deeper in the jungle, there might be new evidence or a new perspective that could challenge or even overturn the current theory. There could be an even more massive tree hidden deeper in the jungle, one you haven't discovered yet. This is the essence of scientific uncertainty and the reason why science can never claim to have absolute truth. Science is like exploring that jungle. It's a continuous journey of discovery where each new finding opens up more questions and possibilities. The unknown is vast and our understanding is always evolving. We can never be 100% certain that we've uncovered every piece of the puzzle or that our current understanding is the complete picture. And that's okay. In fact, this uncertainty is what drives scientific inquiry and progress. In fact, it's more than okay, it's essential for scientific progress. The willingness to question, to doubt, and to remain open to new evidence is what allows science to advance. It's what leads to breakthroughs and new technologies that improve our lives. So, the next time you hear that a scientific theory is not 100% certain, remember that this is not a weakness but a strength. It's a testament to the dynamic and self correcting nature of science. It's what makes science a powerful tool for understanding the world and making it a better place. Embrace the uncertainty, for it is the very foundation upon which scientific knowledge is built. It is through this uncertainty that we continue to explore, discover, and innovate, pushing the boundaries of what we know and what we can achieve.